Lab 5 allowed me to choose my own physics adventure to analyze. I decided to learn more about the world's largest rope swing in Moab, Utah. My model was based upon a person jumping off the top of the arch and swinging from a rope, similar to the motion of a simple pendulum. I modeled this rope swing using physics principles, approximations, and VPython. My final model represented this situation fairly accurately, however, it did not take into account air resistance. Before I began my modeling, I did some research in order to establish some initial conditions. The height of the arch is approximately 150 feet, or approximately 45.72 meters. The length of the rope is approximately 130 feet, or approximately 39.624 meters. The standard spring constant for a rope is 29,000 newtons per meter. I used a weight of 80 kilograms, the average weight of an American male. I used two main physics principles in my calculations, the momentum principle and Newton's second law. We can use these principles to find the parallel and perpendicular components of the force, and thus the parallel and perpendicular components of the change in momentum. The parallel component describes the change in speed of the jumper, while the perpendicular component describes the change in direction of the jumper. According to Newton's second law, the parallel component of the net force is equal to the parallel component of the change in momentum. The perpendicular component is found in a similar way, this time by subtracting the parallel component from the total net force. The remainder is the value of the perpendicular component of the net force. I then incorporated Hooke's law, which says that the force of the spring equals K, the spring stiffness constant, times S, the displacement of the spring. I implemented Newton's second law and obtained a statement for the net force. I also used another statement of Newton's second law to update the position of the person. Now let's take a look at my clip and tracker. I had difficulty finding a video of this rope swing from a stationary camera. Therefore, my video is short and not representative of the complete motion. However, it gives you a good idea of the jumper in action, as well as the course of motion the jumper experiences. Here's the graph of the jumper's position versus time for this short segment. By the idealistic nature of this graph, we can see that it will be most beneficial to create a model based upon a simple pendulum. Now, let's take a look at the model I created in VPython. After setting up some of the initial conditions for my scene, I created a ball attached to a spring to represent the jumper and the rope. I set the value of gravity to 9.8 meters per second squared. I set the mass of the ball to 80 kilograms, and I set the length of the rope to 39.624 meters. The spring constant, Ks, was 29,000 newtons per meter. I used the momentum principle to find the person's initial momentum. Since the person is initially at rest on top of the arch, this value is 0. Then I went into a while loop. I first found the position of the person and the length of the rope. Next, I calculated the stretch of the rope. I entered the spring force and the gravitational force in order to calculate the net force based upon Newton's second law. I then updated the person's momentum and position. This is what the code looks like once it's run. The white arrow represents the perpendicular component of the net force, and the red arrow represents the parallel component of the net force. The yellow arrow shows the net force as a vector. The arrows move proportionally to the magnitude of the force components. For example, at the bottom of the jumper's motion, the parallel component is at a maximum and the perpendicular component is 0. The rope has to be represented as a real rope, meaning it has some stretch. If the rope did not have any stretch, the jumper would not survive due to the forces felt during the jump. The stretch of the rope at the bottom of the swing can be found as 0.0811 meters. The tension of a real rope is greatest at the bottom of the jump. I used Newton's second law to find the force of tension. I summated the forces in the radial plane and I solved for tension. I found a value of 2,352 newtons at the bottom of the jump. I also calculated the velocity of the jumper at this instant using the conservation of energy. I found that the maximum velocity reached at the bottom of the jump is 27.8681 meters per second. I did not take air resistance into consideration when performing my calculations. Therefore, my model will not be completely true to the motion of the jumper. However, it gives a pretty good estimation of the motion. The actual motion will be slowed as the jumper makes his or her way through the bottom of the fall.